Hello everyone! In this video, I will take you through my journey to recreate the Doom engine in Java. First of all, I'm sorry, but I'm not a YouTuber, so this video will not be perfect. I still hope it will be good enough so I can transcribe the process I went through to recreate one of the most iconic game engines. I divided this project into multiple steps, so let's jump straight into the first one. Doing graphics in Java. For the graphic, I decided to go classic and use two main libraries, Swing for the graphical user interface and Graphics for the game rendering. An important note is that I will not be using any built-in function for 3D from Graphics, so I will only rely on line and 2D shape, and I will have to create all the 3D logic. Enough context, let's jump in the development of the game engine itself. And once we have a way to do graphics, the first step to recreate this 3D game engine is actually to build a 2D version of the game. This idea of having a 2D version of the game brings some advantages and disadvantages. The main disadvantages being to not be able to have verticality, meaning that you can't have stacked rooms, and the fact that you can't move the camera upward or downward, but only around the Z-axis, which is called yaw. And one of the main advantages is to be able to use the binary space partitioning algorithm, which we will talk about later. So when it came to the creation of this 2D representation of the map, it was quite easy, since the other part of this project came later in the development. But I needed to be absolutely certain that my implementation was correct, since everything relies on this 2D representation. That's why I spent a lot of time designing how I wanted to implement the game engine. The final design I decided to go with is pretty close to what the original Doom game engine uses, with three main data structures: vertex, vertices, and sector. Vertex represents a 2D point, so it simply has two coordinates, x and y. The vertices are segments between 2 points that represent a wall. An important note to take in consideration at this step is that vertices are oriented from one point to another. So if we draw the normal of those vertices, we can see where the wall is looking and where the collision and texture will be. Finally, the sector is a set of vertices that together represent a closed shape representing a room or an obstacle. And with all three of these data structures, we can easily build the 2D representation. The next step was to implement one of the main algorithms behind the Doom engine, the binary space partitioning, or BSP for short. This algorithm is one of the main reasons that Doom was able to run on almost every computer at the time it was created. The idea behind this algorithm is to divide the map in recursively smaller sections and to form a tree based on those divisions. That tree is fast to traverse and enables to draw rapidly only the section of the map that can be seen by the player in the reverse order from front to back. Here's a showcase on a simple map of how this algorithm is executed. We start with the normal map and select a random wall. Depending on the wall selected, the result will be different and might be more or less efficient. We want to have the least segment possible at the end of the algorithm to have the most effective result. So, once the initial segment is defined, we split all the other segments in two groups, those behind and those in front, and we split the segments that intersect. Then we repeat that until all the segments are splitted and the algorithm is finished. After that, we have a complete BSP tree and we will not need to run this algorithm again. That's the main advantage. All calculus is done once at the start. Now that the 2D map is functional and that the BSP tree is built, the next step was to implement a camera with movement and a field of view. The goal here was to simulate the player's perspective by only rendering what's within the line of sight. To achieve this, I utilized the BSP tree I had already set up. By traversing the tree, I could determine which segments of the map are visible to the player. Only those visible segments were added to the draw list, ensuring that the game renders only what's necessary and keeps the performance optimized. Here's a quick demo. You'll notice that as the player moves, only the segments within field of view are drawn. The next step was to project this 2D view in a 3D representation. The first important point to remember is that thanks to the BSP tree, I don't need to worry about texture overlapping, and I can actually draw everything freely, since the wall will be rendered in the right order from back to front. Next, for every wall, I simply have to take both endpoints of the wall or the intersection of the wall and the field of view lines if the endpoints of the wall are outside of the field of view, and estimate the distance of these 2 points to the player. Now that I have the distance of the 2 endpoints, I need the angle between the endpoints and the line of the field of view. And this angle represents the point where the wall starts in the 3D representation. And based on those 2 pieces of information, I know where the wall starts on the x-axis of the screen, and the height of the wall is based on the distance to the player. And with that, it's easy to draw a polygon of the right shape. For now, we simply draw with a solid color. Once we have that, the next logical step was to add texture to the game. This was difficult, but not as much as I anticipated, since I already had the shape of the polygon that represents the wall with the previous step. I only had to replace the color with the texture, but it wasn't as simple as that, since the texture is a square of 64 by 64 pixels, and the shape of the wall varies and is generally a lot bigger than 64 pixels. To solve the problem of the shape, I simply had to map the image to the wall. Since the wall is always a quadrilateral, like the image, it's possible. But to resolve the problem of the size difference between the texture and the wall, I had multiple options. Either stretch the image to be big enough, which might distort the texture, or tile the image to repeat the texture on the wall, which might lead to having a repetitive pattern. I finally decided to go with the tiling method, and here is how it renders. For the next step, I implemented one of the key features of Doom, portals. Portals work by having 3 different heights. Those heights are stored in the sector data structure and will define the height of the floor, the height of the ceiling, and the height of the end of the ceiling. So it divides every wall into 3 parts: bottom, middle, and top part. Every part has its own texture, and in the final game, a lot of walls actually don't have texture for their middle parts or even all of them. For instance, when drawing a door, you want to have an empty middle texture, and in a room composed of multiple sectors, the linked wall between sectors will not have any textures. This wasn't super hard to implement, since during the designing of this project, I had anticipated it. Finally, I finished by polishing the game. I improved the player movements. In particular, I added camera movement linked to the mouse, which were previously linked to the keyboard. Then, I added a player bobbling animation to reinforce the feeling of movement. I also added the fact that the player height is dependent of the height of the current sector he is in, to see change when entering a sector higher. I also added a weapon at the bottom of the screen to mimic the original Doom, and lastly, I added collision to the wall by calculating if the segment between the current player position and the next player position cross the wall. And that's basically how I recreated the Doom engine. I hope this video was clear and that maybe, who knows, enables someone to create a similar project. If you want more information, you can check the code available on my GitHub in the description of this video. And I thank you for watching this video.